Okay, today we get to talk about some fun applications of ray optics. We're going to talk about cameras and eyeballs. It turns out the camera is really, in principle, fairly simple. It's a fairly simple device. You have something you want to take a picture of, and so you get a lens, you make a real image of that on your detector, which is usually a little CMOS chip or something like that. All right, so it's fairly straightforward how it works. There are a lot of subtleties. For example, we've always used the paraxial ray approximation. Turns out if things are far off the optical axis, like they oftentimes are when we're taking a picture, you have to worry about aberrations, and so they actually typically will make your camera lens maybe out of multiple elements, or make it out of some object that's not actually spherical. Try and correct for the fact that different colors of light focus differently, because the index of refraction is slightly different for different colors. And so they try and correct for all of that in the lens, which makes it a little more complicated. But the basic idea is pretty simple. All right? Now, when you go to take a picture, you may worry about the shutter speed. What shutter speed do you use? And what things affect the shutter speed? All right? It turns out that there are two things that affect the shutter speed. Well, there's several things. There's how much light is actually coming off of your object, right? If you're in a brighter room, there's more ambient light, there's more light reflecting off of Uncle Bill's face, you can use a shorter shutter speed. You get more intensity of light on your detector, all right? But there are also other things that matter. It turns out the focal length of your lens matters, and it turns out that the diameter of your lens matters. Why would the diameter matter? Well, if your lens is bigger, right? So here's this light coming off of the tip of Uncle Bill's nose. If you have a bigger lens, you're going to catch more of that light. So a bigger diameter catches more light, all right? And the focal length also matters, because if you have a very short focal length lens, it will focus to a very small image. The magnification will be very small. If you have a longer focal length lens, the magnification is bigger. A smaller magnification means that the light is focused more tightly, right? And so you take this little bit of light and you focus down right there, you can make very intense bright light, whereas if it were a bigger focus, right, if you have this object and it makes a bigger object on your detector, that light is spread over a bigger area. All right, so it turns out the focal length also matters. A shorter focal length will give you more intensity, so you can have a shorter shutter speed, and a bigger diameter catches more light, gives you more intensity, so you can have a shorter shutter speed. It turns out the distance to your object doesn't matter. I remember when I was a kid, back before cameras, just pretty much every camera had a built-in light meter, a lot of times professional photographers would have a separate light meter that was separate from their camera. And we did a little primary program and got someone from the ward who was a professional photographer to come and take pictures of it. And he had this little light meter, and he'd hold it up to your face. And just by measuring how much light was coming off of your face, he could calculate what shutter speed he needed to use, and it didn't matter how far away he was. He just needed to know how much light was coming off of your face, and then a combination of the diameter and focal length of the lens. It turns out it doesn't depend on these independently. It turns out it depends on the ratio. So we defined this thing called the F number, which is the focal length of our lens divided by the diameter. All right? And a small F number means bigger lens or shorter focal length, which means you get more light, intensity on your detector, and you can have a higher shutter speed. All right? So that's the basic idea. The exposure only depends on the time, the intensity of the light coming off of your subject, and the F number of your lens. All right. A lens with a small F number is known as a fast lens, because it exposes your detector quickly with lots of intensity. All right, now I'm not going to derive this exactly. I'll show you at the end. I'll have an optional derivation where we can show that it doesn't depend on how far away you are. All right, now, but why would you ever want a bigger F number, right? I mean, if you've got this lens here and you're catching all of this light, why would you want to intentionally? You've probably noticed this. If you've ever worked with like a digital SLR, you can set the f-stop of your camera. You can change the F number. And it does that by putting in an aperture, blocking out light, and effectively making your lens have a smaller diameter. Why would you ever want to do that? Why would you want to throw light away? All right, make your shutter speed have to be longer. Well, maybe you're doing some weird effect and you like blurry images, and so you want to throw away light so that you have to have a longer shutter speed and things are blurry. But that's a really off-label use of your camera. It turns out there's a more common use for making a bigger f number, stopping your aperture down. All right, so well, yeah, making a bigger f number. And that's this. Imagine, if you will, that you focused your camera so that the tip of Uncle Bill's nose is right in focus on your detector. But some other object in your scene, Aunt Mabel, she's a different distance away from your camera, so she focuses back a little bit behind your film. She's not quite in focus, right? So she's going to be a little bit blurry in your image because your detector plane, she's not focused right on your detector plane. All right, but watch what happens if I put in an aperture and increase the f number. I effectively make the diameter of my lens smaller. All right, if I block these rays out here, get rid of them, watch what happens. There's less blurring. So without the aperture, there's more blurring. With the aperture, there's less blurring. So by having a smaller f number, by blocking part of our lens, we can make the depth of field of our camera bigger. In other words, kind of the range over which things don't look very blurry, we can make that bigger. So that's why you'd want to increase your f number by putting in an aperture, and that's why cameras have that option typically. Okay, so enough about cameras. One other thing. I'm going to show you a derivation later, but when you figure out the magnification of an image and whatnot on a camera, right, magnification is negative q over p. With a camera, typically you use a very short focal length lens, right? Your camera is typically small compared to the distance between you, your camera, and the thing you're taking a picture of. All right, so P is really big compared to F and Q. So using our imaging equation, if P is really big compared to F and Q, right, in the limit as P goes to infinity, this thing goes to 0, and F is about equal to Q. So when you do magnification calculations and things with a camera, oftentimes you can just not worry about calculating how far from the lens the image forms. You adjust the lens to get it in focus, but that adjustment is typically very small compared to the distance between, you know, your average distance between your image plane and your lens. And oftentimes you can just substitute the focal length for the image distance when you're dealing with cameras. Okay. Now let's talk about the eye. The eye is kind of interesting, all right? You have some object out here and you want to make an image of it. So what do? You make a lens. Well, remember I talked about how earlier I said you could actually make images with just one surface? An eye is kind of like that. It turns out there is a little lens inside your eye, but that lens does not have a lot of focusing power. It turns out it's the cornea that does most of the focusing to make this image. All right, so the cornea does most of the focusing, that just curved surface. And the detector is actually inside the gooey stuff in your eye. It's inside the vitreous, the aqueous humor in your eye. The little crystalline lens in your eye, what it does is it just makes fine tweaks to the focus. There's a little muscle around it that can squeeze it and make it more curvy or relax and make it flatter. And that just adjusts things to try and make the fine adjustments to get your eye to focus an image onto your retina. Your eye is pretty amazing. It turns out, we'll talk about like limitations that wave optics puts on things, and it turns out that kind of the best lens you can make is known as a diffraction limited optic. A healthy eye is diffraction limited. It's like amazingly good. Also, a lot of times we talked about how you get aberrations when you move off axis, you know, when you don't have the paraxial ray approximation anymore. Well, it turns out having a detector which is curved can really do a lot to eliminate aberrations. And so your eye having a curved retina, your eye is just an amazing imaging instrument. You should be in awe of how amazing your eyeball works. All right. Now, when we talk about correcting vision, if you have a problem with your eye and you have to wear glasses, if you go to an optometrist, they probably will not talk about the focal length of the lens. They'll talk about the focusing power, and the units they use are diopters. And just in case you ever see this sometime, you should know the power in diopters, it's just equal to 1 over the focal length in meters. So the unit diopters is really equal to inverse meters. And so a lens with a short focal length has a high power. It has high focusing power. Whereas like a sheet of plate glass, right? A sheet of plate glass that doesn't bend light, right? If I send parallel rays in, where do they meet? Well, they don't get bent. They meet at infinity. So the focal length of a sheet of plate glass is infinity, which means the focusing power is 1 over the focal length, which is 0 diopters. Right? So plate glass has 0 focusing power, infinite focal length, whereas I may have some lens, and maybe my lens has a focal length of 1 meter, which means its power is 1 over f, and that would be 1 diopter. Alright, so it's just another unit, another way to think about focusing power. Okay, so when we figure out how glasses work, it turns out we don't have to worry about what goes on in your eye. Alright, you can just ignore that. What we're going to do is we're just going to say, well, look, I know my eye can see certain things. Let's make sure I know that my eye can see things at certain distances. Let's just think about my glasses making an image out where my eye can see it, if that makes sense. So for example, imagine you're nearsighted. A nearsighted person can see things that are close, but they can't focus on things far away. Things far away are blurry. So for a nearsighted person, we would measure something called the far point. We'd take them to the doctor's office, or the ophthalmologist or the optometrist, and they will measure the furthest away thing that you can focus on, and that is your far point, the furthest point you can see clearly without wearing glasses. And then you will get some glasses that will take an object further away and make an image of it closer to you where you can focus on it. Alright, so imagine I can't see something over here, but I can see something over here. I'll just put a lens on here. I'll just put my lens right here in front of my eye, and I want that lens to make an image of this somewhere in here where I can see it. So what focal length of lens do I need? Well, how far do I want to be able to see away from me? I mean, you want to be able to see things that are infinitely far away. So I've got this distance. Let's call it XFP. That's my far point. That's the furthest away thing I can focus on. But I want to be able to focus on things that are all the way out to infinity. So my object is going to be at infinity. Alright? So I use my imaging equation, and then I say, okay, I know what P is. I want to find what focal length of lens I want. What should Q be? You're probably thinking, well, I've got this object out at infinity. I want to make something at infinity. I want it to make an image of it in where I can see, and the furthest I can see away is my far point. So you're probably thinking Q ought to be my far point. And then you notice I left some space right there, and you think about it and you say, ah, wait a minute. My glasses are going to make a virtual image. Alright, I want the image to be on the same side as the object. So really we want Q to be equal to minus our far point. Alright, so that means 1 over F is equal to, well, we want Q to be equal to negative our far point when P is infinity, when we're looking at things infinitely far away. So 1 over infinity is 0, and this is just 1 over negative my far point. So it turns out the focal length that I need is just minus my far point. So if you are nearsighted and cannot see things far away, you need a lens with a negative focal length, which is equal in magnitude to your far point, the furthest distance you can focus. Now, I read this great book when I was in, well, they made us read this book in high school called The Lord of the Flies. You may have read it. And at one point, they used this kid's glasses to focus sunlight and make a fire. Well, they said he was nearsighted in the book. Well, guess what? If he's nearsighted, he has diverging lenses. He has lenses with a negative focal length. You don't focus light from the sun down to a point and start a fire with a lens with negative focal length. So you better have somebody in your crowd who's farsighted if you want to start a fire. So let's talk about farsighted people, since they're so essential in emergency fire-making situations. A farsighted person is someone who can see things far away. They can see out to infinity. They can focus on things out to infinity, but the nearest thing they can see is not very close. Now, different people can focus on things at different distances, but just kind of by convention we say if you can focus on something 25 centimeters away, you have a healthy eye. So if you are farsighted, that means you can't focus on things that are 25 centimeters away. You have some near point, we'll call it X near point, And that's the closest you can focus. So if you put something that distance away from your eye, you can focus on it. But if you move it closer, things get blurry. All right, so if you are farsighted, you want a lens that will take something which is close to you and make an image at your near point, so something further away so you can see it. So you want, if something is 25 centimeters from your eye, you want your glasses to make an image at your near point. All right, so I want to see something right here. I can't, so I'm going to make an image of it out past my near point. All right, so our lens equation says 1 over f is equal to 1 over p plus 1 over q. We want to know what focal length of lens we need. What is p? Well, the nearest thing we want to see is at 25 centimeters. What is q? Well, we want to take this thing at 25 centimeters, put it out at our near point. So q is going to be equal to x near point, and then we stop once again, and notice the space I left here for a minus sign. And remember, that's right, our glasses are making a virtual image. I want the image to be in front of my eye, not in the back of my head, because my eyes can't see things in the back of my head. All right? Your retina, your cornea and your lens will make an image of that image, which is a real image on your retina. But for the glasses part, it's just making this image out in front of us on the same side as the object. All right? So we plug that all in and we say, well, what does our focal length need to be? Well, the focal length needs to be 1 over 25 centimeters minus 1 over our near point to the negative 1. All right? And now, we know that our near point, if we're farsighted, our near point is going to be greater than 25 centimeters. So 1 over our near point will be less than 1 over 25 centimeters, and our lens then that we need will be one with a positive focal length. So if you have a friend, or if you are farsighted, your glasses can be used in a wilderness survival situation to start fires. Be comforted with that. All right, so that's how you would prescribe lenses, and that's what an optometrist or an ophthalmologist would do. You go in there, and they'll basically measure what your near point is or what your far point is, and figure out what lens you need. Now, myopia is the fancy doctor name for nearsighted. Hyperopia is the fancy doctor name for farsighted. All right. Now, but not everybody is just nearsighted or farsighted, right? So a nearsighted person, their eye's just out of adjustment. You can give them some glasses, and now they have normal eyesight with their glasses. Same thing with farsighted. But if you're like me, I have presbyopia, and what that means is I have a limited range because I've gotten really old and my body is breaking down. I'm becoming more pathetic every day, and so my eyes no longer can focus over as wide a range as they did. The crystalline lens in my eye is starting to get a little stiffer. All right? And so without my glasses, I can focus on things at infinity, but I can't focus on things that are close. And so I can measure my near point, figure out what glasses I need, but when I put those glasses on, now I can see things that are near, but I can't see things far away. So people with presbyopia, oftentimes they'll have glasses with multiple focal lengths. All right? In the old days, they would have bifocals, where your glasses are split down the middle. The bottom part is designed for reading, the top part is designed for looking far away. Nowadays they make lenses that actually gradually change their focal length from top to bottom. All right? There's also kind of other weird things that can happen to your eye, like something called astigmatism. Astigmatism means that the focal length of your cornea and your crystalline lens are different in different directions. So to correct that, you actually need a lens that is not spherical. It's like got a different radius of curvature. You know, if I'm looking down on my lens, if I rotate my lens over, maybe it's got a different curvature if I rotate it 90 degrees. So you have a lens that's not spherically symmetric to correct for that. So there's all kinds of funny things that can happen to your eye. You could, I don't know, have a mode in it or something, right? But we're going to stick with just myopia and hyperopia for our calculations in this class. All right, now that is everything that you really need to know. If you want to stick around for a few minutes, I'm going to show you really quick proof why the exposure time on your camera doesn't depend on the distance between your camera and the thing you're taking a picture of. All right, so the intensity on your film, I'll call that I prime, that is what determines how long you have to do an exposure, right? Your film. I keep saying film. Nobody uses film. Hardly anybody uses film. Some people use film, but you probably don't use film. The intensity on your detector, right? That's what determines how long your exposure needs to be. So if I take this pixel, how much light is entering that one pixel? All right. But the intensity on that pixel is going to depend on the intensity of light being reflected or emitted off of the surface, that you're taking a picture of. You're taking a picture of me, you look at the pixel for the tip of my nose, how much light is coming off of the tip of my nose, all right? So it's proportional to that, but not all of that light gets into your camera, right? So your object is over here, the light's coming off, and it's spreading out like a spherical wave, right? So the amount of light that actually gets to your camera, it gets caught by your camera, that intensity is going to drop off as 1 over the distance squared. Of course, the distance is p, so 1 over p squared, right? You believe me? Okay, but then you've got your lens right here that's catching that light. The bigger your lens is, the more of that light you're going to capture. All right? So you've got some intensity of your light that drops off as 1 over p squared, but then you're catching it with a lens which has got some diameter d. The surface area of that lens is proportional to the diameter of the lens squared. All right? So that tells you how much light you're capturing, right? But it also matters what your focal length is. If you focus really tightly, you take all this light you capture and focus it to a tiny spot. Maybe you take all the light that's coming from this blob right here and focus it to 1 pixel, right? Then maybe you don't need a long exposure because you're putting a lot of light on that 1 pixel. But if your lens has a longer focal length, maybe this blob, this black head on the end of my nose images to a bigger spot that covers multiple pixels, and so I get less light on any 1 pixel, and I need a longer exposure time, all right? So the intensity of light on a given pixel is going to be inversely proportional to the magnification squared. Why squared? Because it's spread out this way and spread out this way, right? And the magnification is how big a linear dimension changes, but your film is a two-dimensional thing, your pixels are two-dimensional things, your image is two-dimensional, so you have to worry how it expands in this direction and this direction. So the intensity on your pixel is going to be inversely proportional to the magnification squared. Well, what is the magnification? So let's copy this over here. Boom, 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 boom. But magnification is just negative q over p, right? Squared. So that cancels with that, and we're left with the intensity at your subject times d squared over q squared. But remember what I said earlier, that for a camera, typically p is very large compared to f, which means that if I look at 1 over f is equal to 1 over p plus 1 over q, if p is really large compared to f, this is going to be small compared to these two, and 1 over f is going to be about equal to 1 over q, and q then is about equal to f, so I'm just going to go and replace q with f here, so this is about equal to I times d squared over f squared, and this is just equal to the intensity of light coming away from your subject divided by the f number squared. And p totally dropped out, you don't need it, it only depended on how much light's coming off your subject that we could measure with a meter right shoved up in their face if we wanted to, and the f number of your lens. And we're done.